Ligand field theory builds on the crystal field theory by incorporating aspects of molecular orbital theory. It was invented by Harry Gray to explain the electronic structures of certain coordination complexes. Gray also developed the idea of the oxo wall, which refers to the maximum number of d electrons in certain oxo complexes. The main way ligand field theory differs from crystal field theory is that you can't consider all ligands as just point charges anymore. Some ligands have bonding interactions with the d orbital of the transition metal that needs to be accounted for. The interactions result in bonding and anti-bonding orbitals, and even pi bonds between the metal and a ligand. There are two main types of ligands that are of interest in ligand field theory: pi-donating and pi-accepting ligands. As the names indicate, pi-donating ligands donate electrons to the metal d orbitals to form pi bonds, while pi-accepting ligands have empty orbitals which accept electrons from the metal's d orbitals to form pi bonds. These are most easily explained with examples. For this video, I will be using porphyrin as a platform for our ligand field theory arguments. Porphyrin is a flat ligand with 4 nitrogen atoms at the corners of a square. It carries a -2 charge as a ligand and binds a variety of metal ions at the center of the square. Porphyrin occurs naturally in heme, which has an iron 2 in the center of the molecule, and is responsible for transporting oxygen in blood. A porphyrin complex is generally square planar unless additional ligands join in from the top or bottom. In hemoglobin, the iron atom is also bound to the amino acid histidine, which in turn connects to the rest of the protein. Before any oxygen or carbon monoxide bind to the iron is sort of pulled out of the porphyrin plane by the histidine. But once it bonds with a ligand, it moves back into the plane and we have an octahedral complex. However, the orbital splitting diagram of the carbon monoxide complex is different from what we might expect from the crystal field theory. So let's continue to use carbon monoxide bound heme as an example. Here I've just drawn the porphyrin as a circle. In crystal field theory, we would split the d orbitals in a standard octahedral complex into two groups of degenerate orbitals. In ligand field theory, we consider the anti-bonding pi orbitals of the carbon monoxide, which line up with the dxz and the dyz orbitals of the iron and pull these down in energy. 4 electrons from the iron will occupy these now pi bonding orbitals, and so we call carbon monoxide a pi-accepting ligand. As I said, pi-accepting ligands have empty orbitals which can overlap with the orbitals of metals and accept electrons from the metal via pi bonds. Pi-donating ligands also have orbitals that can form pi bonds, but these ligands provide the electrons responsible for the bonding. Typical examples of pi-donating ligands are oxide, nitride, carbide, and imide, and the atom that bonds to the metal has a complete octet like neon. Anions like oxide will use their p orbitals to form bonds with the metal. If we define the metal oxide vector as the z direction, then the oxygen pz orbital will bond with the metal dz squared orbital to create a sigma bond, which will be very low in energy. And the oxygen px and py will overlap with the metals dxz and dyz respectively, forming pi bonds, which will also be low in energy but not quite as low as the sigma bond. Since the oxide orbitals already have 2 electrons each, we'll use them to fill the bonding orbitals. We'll add the metal d electrons into the higher orbitals later. Let's consider the d orbital ordering of a d0 metal center first. Titanium 4-oxoporphyrin is a good example of a stable complex with a d0 metal. First, the x squared minus y squared d orbital will be high in energy as it points directly towards the 4 nitrogen atoms of the porphyrin. Next, the dxy will not be pointing directly towards any ligand. The dxz and dyz will overlap sideways with the oxygen's px and py orbitals, creating 2 pi bonding orbitals, which will be lower than the dxy in energy. Now, whenever we have bonding orbitals, we also have anti-bonding orbitals, the pi star orbitals. These will be high in energy, though not as high as the dx squared minus y squared orbital. And finally, we have the sigma bonding orbital, created by the head-on overlap between the dz squared orbital of titanium and the pz orbital of oxygen. This bonding orbital will be very low in energy, and this interaction also creates an anti-bonding sigma star orbital that's very high in energy. Now we can start filling in the electrons, starting with the oxide's 6p electrons. These will fill the sigma bonding orbital as well as both the pi bonding orbitals. Since we've chosen a complex with a d0 metal, there are no more electrons to fill, We therefore draw the complex with a triple bond, as we have 3 bonding orbitals filled. But what if we had a D1 metal, such as chromium 5 nitridoporphyrin? As before, the 3 bonding orbitals are filled with electrons from the ligand, and when we add the electron from the metal, it gets added to the dxy orbital, as this is the next lowest orbital in energy. If we replace the nitride with oxide, the chromium becomes chromium 4, assuming the molecule's overall charge is still 0. And we have another electron to add. So now we have 2 electrons in a dxy orbital. Note that the dxy orbital has no impact on the metal-oxygen bond, so that it's still a triple bond. Now let's consider an iron 4 porphyrin bound to an oxide ligand. The iron-oxygen bonding orbitals still look the same, and the electrons from the oxide are still filling them up. Since the iron is D4, it has to start filling the pi anti-bonding orbitals, putting 1 electron in each of them. Considering the bond order now, we have 3 filled bonding orbitals and 2 half-filled anti-bonding orbitals, resulting in a bond order of 2, so we draw the bond between iron and oxygen as a double bond. This example introduces the concept of an oxo wall. For a square pyramidal or octahedral complex, each anti-bonding pi orbital can at most have 1 electron each. Any more and the complex would be too unstable. So the result is that for any square pyramidal or octahedral complex with an oxide or nitride or similar axial ligand, you can at most have a D4 metal, which puts a wall between group 8 and 9. As a matter of fact, even the iron 4 oxoporphyrin is unstable and highly reactive. The enzyme cytochrome P450 uses an iron 4 oxo to oxidize a variety of toxins and other undesirable molecules. There are ways of sort of circumventing the oxo wall, such as resorting to other molecular geometries other than octahedral and square pyramidal. Different geometries lead to different energy level diagrams. For example, a cobalt with a tris pyrazolyl borate and an imido ligand has a pseudo-tetrahedral shape. Here, the dx squared minus y squared orbital isn't pointing directly towards any ligand, so it will be exactly alongside the dxy orbital in energy, making more slots for electrons before the anti-bonding pi star orbitals need to get filled, meaning that the cobalt 3 complex, which is d6, can exist with these ligands. The ideas I've gone through can also explain metal-metal bonding. You can have both sigma and pi bonds between the d orbitals, and if they're correctly aligned, we can also have something called a delta bond. Let's look at an example of this tungsten porphyrin dimer. Tungsten 2 is a d4, meaning we have a total of 8 electrons to place in our molecular orbital scheme. The dz squared orbitals overlap head-on, creating sigma and sigma star orbitals. The dxz and dyz orbitals overlap to create pi and pi star orbitals. And finally, the dxy orbitals, which are along the plane of the porphyrin, can be in phase and overlap, creating the delta bond and anti-bonding orbitals. All 4 bonding orbitals are low in energy and are all completely filled up, resulting in a quadruple bond. If we had something like a rhenium-2 porphyrin, where rhenium-2 is a d5 metal, the anti-bonding delta orbital would also be filled, making the bond order 3 again. The delta bond is weak, however, and the energy gap between the delta and delta star is small. So, both tungsten porphyrin dimers and rhenium porphyrin dimers have a similar metal-metal bond lengths.